Hi everyone, this recording is going to be a little different. You'll notice, this is the second time I've done it for statistics, where I do a different feature. The first lesson we did Microsoft Excel. This lesson I'm going to show you some examples to help you understand what a normal distribution is, which is our topic of today, and where in real life instances you do see it. Okay, so it's not something that is purely theoretical. So like I said, this lesson focuses on what's called the normal distribution, and it's one of the most important and widely used distributions in statistics. One of the major reasons for it is because we do see it in things we do in our everyday life. This normal distribution is seen, and you can see it as a bell curve. Okay, you might have heard riding the curve or the bell curve for grades. That's kind of, that's where this term, you might have heard that term from. And this curve can take different shapes. It can be very flat, okay, or it can be very steep. But there's a couple key features about this curve that are consistent among all of them. The first is the very peak of this curve, the vertex point, that is the mean value of your whole set of data. Okay, that mean value is known as mu. Okay, you're going to see that used a lot. And what this distribution shows is on each side of that mean value, it's normally distributed, meaning 50% of the data falls on one side of the mean and 50% falls on the other side. So these are symmetrical. If you were to cut this in half and fold it over, okay, like you would a piece of paper, they would match. Okay, so both sides of this curve, the area under it, this entire space here, is identical. Okay, that's going to be important when we talk about terms later on. And it doesn't matter what size this curve is, it'll always be symmetric. So those are some key points to know. Okay, so just to reiterate those, right? Give me a second, I'm just changing colors. So to reiterate these points, the mean is the center of this. Okay, it's symmetric on both sides of the curve. All right, and when we talk about normal distribution, it's continuous, right? So you should be able to calculate at every single point on this curve. We're going to look at percentage of observations that fall within each of those pieces, okay? So a normal distribution, in the way that you're normally going to see it, you'll probably see my screen move a little as I'm changing colors of pens and whatnot, because this is a little different setup. For a normal distribution, what we have is we use the mean and the standard deviation. Remember, we talked about the standard deviation in our last lesson. And we can see how many observations fall within 1, 2, or 3 standard deviations of the mean. So, like I said here, this is a normal distribution. So the mean is here in the center. You see it listed as mu. The standard deviations notation, okay, sigma, is the same that we saw in our last lesson. So a couple important items to note about the standard distribution, or normal distribution, is if you have one standard deviation away, okay, so let's say that the average grade was 10 out of 15. One standard deviation away could be sigma is equal to 1. So what that means is that if you were one standard deviation above the mean, you scored 11 out of 15. And if you scored one standard deviation below the mean, you scored 9 out of 15. And if you go 2 standard deviations, it would mean you scored 8 out of 15. Okay. If you scored 1 standard deviation, I should say 15, 3 standard deviations away, you'd get 7 out of 15. Going the other way, if you were 2 standard deviations above the mean, you scored 12 out of 15. And 3 standard deviations, you scored 13 out of 15. And if the grades are perfectly distributed, so they follow a normal distribution, what this means is, for 1 standard deviation from the mean, so scores between 9 and 11 out of 15, 68%, or approximately 2/3 of the class, scored around that. So, if you were to talk to 2 more of your friends, and let's say you scored 10 out of 15, one of them is likely to have also scored between 9 and 11 out of 15 on the test. Okay, so that's what it means by a normal distribution. 2 standard deviations from the mean, again, you notice that this curve gets shorter and shorter, meaning less and less observations fall within that, or to the other side of it. So if you're within 2 standard deviations of the mean, meaning you scored between 8 and 12 out of 15, 95% of people in the class would have scored that. So it's very, very likely that almost all of your friends, probably 9 out of 10 of them, scored somewhere between that score of 8 and 12. When you get to 3 standard deviations from the mean, you're at almost 100% of your values, almost every value. You're at 99.7% of values would fall within it. And this, remember, is if data is normally distributed, okay? If your test doesn't follow a normal distribution and the grades are all over the place, this isn't applicable. But in other areas, you'll see that it actually does happen a lot more often than you think. Okay, so these numbers are important numbers to know when you talk about a normal distribution. So 1 standard deviation is 68% of values, or I guess data. 2 standard deviations is 95%, and 3 standard deviations is almost 100%. Okay. So let's look at an example of what that means. So if the mean temperature for August is 26.9 degrees Celsius with a standard deviation of 3.2 degrees Celsius, find the upper and lower temperature limits that fall within 1 and 2 standard deviations of the mean. So if it helps you to visualize this, I'm going to draw a graph here. Okay, and we're going to have our normal bell curve. That's a normal distribution. And remember, the center point of it is our mean mu. Okay, so our mean here was given as 26.9 degrees C. Our standard deviation, sigma, is 3.2 degrees C. So when it asks you to find the upper and lower temperature limits for 1 and 2 standard deviations from the mean, what you're looking at is a point here, which is mu plus your standard deviation, and a second point here, which is mu plus 2 times your standard deviation. And remember, because this is symmetric around the mean, you have to do it to both sides, because only 50% of the data is on one side and 50% is on the other side. So we have to go again on the other side and do mu minus the standard deviation, sigma. Okay, so it becomes mu minus sigma. And our second one is mu minus 2 sigma, okay, because we're going 2 standard deviations from the mean. So looking at this, okay, that means if we want to calculate the upper and lower limits, for 1 standard deviation, we have mu plus sigma and mu minus sigma, which is 26.9 degrees C plus our standard deviation of 3.2 degrees C, which gives us 30.1 degrees Celsius. That's the upper limit, right? Because it's a temperature higher than the mean. The lower limit, mu minus sigma, is equal to 26.9 degrees Celsius minus that standard deviation, 3.2, which gives us 23.7 degrees Celsius. Now, if this is normally distributed, that means this is one standard deviation from the mean, and 68% of the time, your temperature should fall within this range in August. Okay? If we go 2 standard deviations from the mean, we have mu plus 2 times sigma, and mu minus 2 times sigma. Okay? And that's equal to 26.9 degrees C plus 2 times the standard deviation, 3.2 degrees Celsius, which gives us 33.3 degrees C. Mu minus 2 sigma is 26.9 degrees C minus 2 times the standard deviation, again, 3.2 degrees Celsius, which gives us 20.5 degrees Celsius. Again, if this is a normal distribution, 95% of our temperatures would fall within this range. Okay? And you look at this example and you start to think that makes sense. How many days in the month of August do you have that are above 33 degrees Celsius? And how many days do you have that are below 20.5? Not that many, right? Okay, you might get part of a day, half a day, maybe. Okay, so you can start to see that if it's normally distributed, the further away you get from the mean, okay, you don't have to get very far away from it for it to count for almost all of the values in your data set. Okay. Okay, so an example of where a normal distribution is used. This is part of a craps table. If any of you have seen a craps table, it's the very long one at the casino, and very intimidating at first glance. But every piece on here, the odds that are created, the payouts are all entirely based on the fact that dice, when rolled, multiple times, show a normal distribution. And that's because when you roll a set of 2 dice, it's more likely to roll something like a 7 because there's multiple options. You can roll a 6 and a 1, or a 1 and a 6, 2 and a 5, a 3 and a 4, 4 and a 3, etc. Okay, so just to kind of illustrate that, I have a craps table. But first, we're going to look at simulating rolling dice. So what this is here is when I click this button, it's going to roll the dice 100 times. And it simulates how often each of these values are rolled. So you're rolling 2 dice, and you can either get, a 2, 3, 4, all the way up to 12. Okay, so 2 being, least likely because you have to roll 2 ones. 12 also being the same probability because you have to roll 2 sixes. And what you'll see is as you get to the numbers in the middle, when you roll it 100 times, so if I click this, okay, as you click it, you see that the overall trend remains to be a curve shape. And it isn't necessarily all the time, because there could be odd instances where you roll more of a certain number. That isn't a real thing that could happen. But from a probability standpoint, it's less likely to happen. So as I keep clicking this, every time I click it and it changes, it's simulating rolling 100 dice. You can see that the distribution remains more or less like a bell curve. There might be instances, see in this case, where the number 8 in that 100 was rolled more often, so 14 times versus 12. And again, that is an instance that can happen. But as you continue to click, you see that that bell curve shape comes back. Okay, so with enough dice rolls, as I click this more and more, you'll see that overall, the 7 is the number that's rolled most often. Okay, so that is very important when it comes to the game of craps. Okay, so just to give you some basics on it, your initial bet, most people start by putting a bet on this pass line. And the pass line is betting that you're at that stage in the game going to roll a 7 or an 11, a 7 being the most likely. Okay, if you roll if the 7 is rolled by whoever's rolling the dice, or an 11, you win. If a number that's sitting up here, 4, 5, 6, 8, 9, or 10 is rolled, then that number is known as on. Okay, so you're trying to roll that number again. All right, so obviously the best number to have would be 7, which they don't have, but they have a 6 and an 8. So going back to here, you see 6 and 8 were also far more common to be rolled than other numbers. Then after that in order, a 5 and a 9. Okay? So what you see here is that's exactly how it's broken up. The payments for each of these numbers are increasingly more. Okay? So if you bet on rolling a 6 or an 8 next, you'll win less than if you bet on a 5 or a 9. And that's because you have a more likely chance of winning. The same thing is true. You'll win more if a 4 or a 10 is rolled and you bet on one of those than if 5 or 9 or 6 or 8 are rolled. All of those use the properties of rolling dice and the fact that it's a normal distribution. Okay, so craps overall actually has one of the highest odds at the casino in terms of winning. So if you're ever just want to have some fun and try learning how to play it, give it a try. It's actually one of my game's personal favorites. I don't go to the casino very often, but when I do, it's very fun to play. So it's just a good example to show you for a normal distribution. The second one that I have to show you, for those of you that have seen The Price is Right back when it was Bob Barker, or now, when you see the episodes of Drew Carey, is Plinko. Okay, everybody gets excited when they play Plinko. And again, it's an example of a normal distribution. You see the most likely scenario for you to roll here is, or for you to obtain, is actually the $10,000 piece. But it's complicated by several factors, and I'm going to kind of show you why. So again, and I have another tab here that shows you a board like the Plinko board. The difference being the Plinko board actually goes all the way up on both these sides here. And what this is going to show is if you start right from the center and you drop balls down in unison, you'll start to see, and we'll hit play. Okay, I'll speed it up so it goes a little bit faster, that they're just following kind of random for the first several. Okay. As more and more and more of them are rolled, you can see the values in the middle are increasing. Okay. So if I speed it up even further, we're only at about 45 balls that have fallen in, but it's already starting to show a pattern that's resembling a normal distribution. You can see the values at the end are actually the least likely. Okay. So, scrolling back up. If I speed this up even more and continue to add more, as you can see, it's continuing to cycle up, the distribution is starting to get more and more and more like a bell curve. Okay? If we continued this, you'd see this trend just grow. So I'll hit pause. The last few will fall down. And so now you're probably asking, why then is $10,000 sitting in the middle? It tends to be the most likely. Well, in this version, it's a little more complicated. They've added other variables. In the example here, everything started on this first peg. You can see that it increases by 1 peg each time. Here, you have an option of putting it anywhere, right? So it changes the dynamic. So it's not quite a normal distribution anymore. So depending on where this person places it, how fast they drop it down, that all affects how it's distributed here. Okay? Given enough tries and placed in the exact same spot here, it would likely resemble a normal distribution, and you'll probably see more often than not hitting the $10,000 piece. But as you saw here, if I restart this and I start from the start, as you're doing a couple values, what you see here is it's not necessarily a normal distribution yet. It's kind of going in all different places. It's not quite, in this instance, we have some in the center. But when you're only throwing 2 or 3 down, it wasn't a normal distribution where all of them were ending up in the center. Okay? So again, all these games like this are playing probabilities and these normal distributions. So I just wanted to show you 2 different examples where you can kind of see them in real life. Okay? So, like I said, okay, I want to bring the slide back up before we move on. For a normal distribution, we talk about being 1, 2, or 3 standard deviations from the mean. And like I said, these values are important. As we kind of move forward, you're going to see where they kind of start popping up. So in terms of normal distributions, one that we often see is known as a standard normal distribution. The reason it's standard is because if you look here on the right, this is a standard normal distribution on the x and y axis, and the mean is actually 0. So we have it centered about this y axis. And for ease in a standard normal distribution, the standard deviation is actually 1. Okay? So if you go 1 to the right, that's actually 1 standard deviation. 1 to the left, 1 standard deviation. 2 to the left or right is 2 standard deviations. 3 to the right or left is 3 standard deviations. So it allows us to form a basis to start our calculations. What a standard normal distribution is going to help us do is it's going to help us look at finding, let's say for instance, right, we looked at 1 standard deviation away. What if our value is sitting right here, or right here, or somewhere over here? How do we know what that percentage is? We know that 1 standard deviation is 34% on either side of the mean, or 68% total. Remember, because it's split in half. So what if we want to know this point? Okay, is it 24%? Is it 27%? Is it 15%? Okay, how do we know that? And we use the standard normal distribution and we calculate what are known as z-scores. Okay, so a z-score helps us to determine what percentage we are from that mean value. Okay, so we're sitting here, okay, again, a standard normal distribution. And when you calculate a z-score is whatever value you're trying to find the percentage of minus the mean mu divided by the standard deviation. And it will give you a value for z. Now we're going to take that value and look in a table to find the data. So what it finds actually is the area here. Okay, remember I talked about areas at the start of this lesson. So the value that's going to come out with that z-score is going to be that area, which is the percentage of values between the mean and whatever value you're calculating. Okay, it's an important item to look at further. Again, this formula, as well as the table you're going to see on the next slide, will obviously be provided to you on the test. And we're going to look at some examples of how it gets used. So, looking at z-scores. For each one of these, the z-score that you calculate will correspond to a certain amount of area under the curve. So let's look at a z-score of 0.1. Okay, these z-scores can be positive or negative. So this is valid for positive 0.1 and negative 0.1. We'll get into what those differences are when we do examples. But a z-score of 0.1, that puts us, just past the mean here, which is 0, okay, or the middle value. So if you look here, that's finding the area, okay, from the mean value 0 up into that point 0.1, okay? So there's a little sliver of area. Now we don't calculate that. That would be calculated by integrating, which we're obviously not going to do in this course. but you get a value of 0.0398. Okay? So thinking back to percentages, if you converted that to a percentage, 0.0398 times 100% would give you 3.98%. Okay? What that actually means, 3.98%, is that only 4% of values fall within the mean in that piece. If you want to talk about everything from that score to the left, you'd have that 4% plus everything here, okay? Which again, remember, it's symmetrical, so that's 50%, okay? So we're going to do some calculations with these. Again, we're going to calculate a z-score, and then what you do with that is you find the z-score and you take its corresponding area calculation when you're actually looking at problems, okay? So let's look at our first example. I really want to show you how to use this, because you might have saw that table and thought, whoa, that's a lot of values. But when I break down what exactly that means, in terms of a real example, it's going to be a little bit easier for you. The lifetime for watch batteries can be estimated with a normal distribution. The mean lifetime is mu is 400 days, and the standard deviation sigma is 50 days. For a sample of 5,000 batteries, determine how many batteries are expected to last A, between 360 and 460 days, B, more than 320 days, and C, less than 280 days. So looking at this, I like to provide the normal distribution here on the right. So our mean here is 400. And our first question is asking how many batteries are expected to last between 460, which would be to the right of the mean, and 360, which is to the left of the mean. So what we want to know is all the values that fall between this. Okay? So what percentage of values is this piece here that's inside this area calculation? Okay? To do that, we calculate the z-score at each of these values, 360 and 460, and we use that to determine how many batteries fall within this range. So I'm going to erase these just to make it a little bit easier. We'll leave the lines here so you can see them. So for part A, we have two z-scores to calculate, if x is 360 days or 460 days. So remember, it's x minus mu over sigma. Mu is 400 days, and sigma is 50 days. Remember, sigma is the standard deviation. So for 360 days, we have 360 minus our mean, which is 400. Divided by our standard deviation, which is 50, which gives us negative 0.8. And for our second option, we have 460 minus 400 divided by 50, which gives us 1.2. So going back to this chart here, we have 0.8 and 1.2. So 0.8 is 0.2881, and 1.2 is 0.3849. Okay, so for this one, we're going to write for 0.8, okay, 0.2881, and for 1.2, 0.3849. So what that is, 0.3849 is this area here in terms of percentage. Okay, sorry, 0.2881. So for 360, 0.2881 is the area to the left of the mean. For 1.2, 0.3849 is the area to the right of the mean. So if we want to know all the batteries that would last between 360 and 460 days, we add those z-scores together. So if we do that, we get 0.2881 plus the second piece, 0.2881 plus 0.3849. And if you add those up, okay, you get 0.673. So that means 67% of batteries should last between 360 and 460 days. So if we take that and multiply it by the total number of batteries, we get 3,365 batteries, meaning that amount of them, which is approximately 2/3, should last between 360 and 460 days. Part B, we're looking for more than 320 days. So I'll erase this so we can look at it again. So we're looking at 320 days, which is somewhere over here. And we want to know all of this percentage, right? Everything that's going to last more than 320 days. So remember, our z-score, if we use 320, is going to calculate this piece. But what we know is that it's perfectly symmetrical across that mean. So the other half of this is 50%, because we want to know all of it, every battery that would last more than 320 days. So we know that we have 50% of them will, because it's on the other side of the mean. And we need to use the z-score to figure out what the percentage is on the other side of the mean. So to do that, our z value is equal to x, which is 320, minus our average, 400, divided by our standard deviation, which is 50. Okay? If you calculate that out, you get negative 1.6. Going back to our chart here for 1.6, again, it doesn't matter if it's positive or negative. We get 0.4452. So going to this question here, that means we have 0.4452, and we add the 50% from the other side, which converting to a decimal is 0.5. So that adding those up gives you 0.9452, or almost 95% of the batteries should last more than 320 days. If we multiply that by 5,000 batteries, again, because there's 5,000 in our sample, it means that 4,726 batteries should last more than 320 days. Part C is looking at less than 280 days. Okay, so going back to this example, erasing these, we have 280 days somewhere over here. Again, our mean is 400. So we want to know if they're going to last less. So we want to know this little piece here. And we can find that by actually finding all of the data all of the value to the right of it and just subtracting that from 100%, because then we're left with just the piece that wouldn't last 280 days. So we find our z-score. It's 280 minus the mean, which is 400, divided by the standard deviation, which in this case is 50. And for this one, we get negative 2.4. Going back again to here, for 2.4, we get 0.4918. So going to here, we get 0.4918. And remember, we're going to add everything to the other side of the mean, which adds 0.5, which is 0.9918. Now that's everything that would be more than 280 days. And we want to know less. So we actually just subtract that from 1 to figure out the percentage that is less than 280 days. So we do 1 minus 0.9918, okay, which gives us 0.0082, right? And then multiplying that by 5,000, we get that only 41 batteries should last less than 280 days. Okay, so this is what z-scores are really used for. You're trying to look at that probability, and in this case, for quality control, how many batteries that you create in this instance are not going to fall within that normal kind of quality assurance range. Okay, how many of them are going to fail prematurely and how many of them are going to overperform? Okay, can you use these as just estimates? All right, so our second example, again, just to show you how to use this Z value properly. Your winter tires have a mean lifetime of 100,000 kilometers and a standard deviation of 10,000 kilometers. For a sample of 2,500 sets of winter tires, determine how many tires are expected to last between 80,000 and 105,000 kilometers, more than 120,000 kilometers, and more than 90,000 kilometers. Okay? So again, I like to have our normal distribution here on the right. Remember, our z-scores are going to let us calculate or give us the percentage of area under this curve. And one thing I've talked about so far is the total area under the curve, keep this in mind, is equal to 1. Okay, so you saw that in our previous example, in our last piece when I was looking for just a tiny sliver of area, and we did 1 minus all of this area here. Okay, so again, once again, we're going to look at using this when we look at this example. So we know that our mean is 100,000 kilometers, how long your tires are expected to last. Your standard deviation is 10,000 kilometers. Okay, so for part A, our z-score is x minus mu divided by sigma. So for our first instance, we have 80,000 kilometers. So 80,000 minus 100,000 divided by 10,000. Okay, so that gives us a value of -2. Our second z-score for part A will be 105,000, or the upper limit, minus 100,000, divided by, again, our standard deviation, which is 10,000. Okay, calculating that out, you get positive 0.5. So once again, we're trying to find these areas under the curves. So we go back to our z-scores here. Our first one was -2. Remember, it doesn't matter if it's negative or positive. So we look at 2, and we have 0.4772. Okay, so going back here, put 0.4772. Our second one was 0.5. So once again, going back to our slide showing that, for 0.5, we have 0.1915. So 0.1915. So remember, that is looking at if our mean here is 100,000. Okay, we have 80,000 sitting over here and 105 sitting somewhere in there. So the first z-score of 80,000 is giving us this area here. Our second score of 0.1915 is giving us the area here. Okay, so we can add those up to get the total amount of values that should be included here. So if we add those two up, we get 0.6687, again, approximately 2/3, right? 66.87%. If we multiply that by 2,500 tires in the sample, we get 1,672 sets of tires, okay? So about 2/3 of the tires should last somewhere between 80 and 105,000 kilometers. For part B, we're looking at more than 120,000. So again, starting here, I'll erase these values that I have written here. We have 100,000. And now we're looking somewhere over here at 120,000. So we're looking for tires in this kind of upper echelon that are going to overperform and last for more than 120,000 kilometers. So, we do expect that to be a small number. How we do that is we calculate the Z-score for 120,000 kilometers, which gives us this area here. And then remember, since this is broken up in half, okay, so it's symmetric across that mean, we add the 50% that's sitting to the left of the mean, or 0.50 for the left side. So starting with our Z-score, we have Z is equal to 120,000 minus 100,000 divided by 10,000. Okay, so that gives us positive 2. And again, we can go back to our table to look, but from our previous example, we had a negative 2 here. And again, it doesn't matter if it's negative or positive. So our value is 0.4772. Okay. Now remember, that's just for the spot to the right of the mean, because 120,000 is to the right of it. So we have to add everything from the left. So we add the 0.5, and we get 0.9772. Now, if we want to know how many tires are going to fall above that, remember, we only want the little sliver there. Okay, we don't want the 97.7% that doesn't fall above 120,000 kilometers. So we do 1 minus the value we calculated, 0.9772. So it's a 0.0228, or, just over 2% of tires, 2.28%, if you were to convert that to a percentage. Multiplying that by 2,500 samples, and we get that about 57 sets of tires out of the 2,500 would last more than 120,000. So we didn't get that many tires, and we shouldn't, right? Because the mean is 100,000, and it's normally distributed. For question C, we're looking at more than 90,000. Okay, so once again, we're going to look at this, but kind of on the flip side. Okay, so again, I'll start by erasing all this so we can start from the start. If I can erase it all. So 90,000 sits somewhere here to the left of the mean. We want everything more than 90,000. So when we do our Z-score, that's going to give us the area from the mean to 90,000. And then remember, since it's symmetric, we're going to add everything on the right-hand side of the mean, because we're looking for more than 90,000 kilometers. So we're going to add the 50%, or 0.5, after we find the first Z-score. So our Z-score is equal to 90,000 minus 100,000, the mean, divided by our standard deviation. And that gives us a value of -1. If we go back to our table, it doesn't matter, again, if it's negative or positive. For a value of 1, we get 0.3413. So we're going to go back here, put in 0.3413. Now remember, we have to add everything to the other side of this curve. So we have to add 0.5. And if we do that, we get 0.8413, or about 84% of tires should last more than 90,000 kilometers. So if we multiply that by our sample, which is 2,500 sets of tires, we get 2,103. Okay, so once again, go through these examples. Understand that these Z-scores are used to find the percentage of values that are falling inside that range for our data set. Okay. So that was all I had for this lesson. One thing you've probably noticed is you might notice the screen kind of went black for a second, but you could still hear me talking. That was entirely normal, so don't think that it was your computer. My tablet was just having a hard time keeping up, so sometimes the screen would blank for a second. There was nothing I could do to kind of remove that. This is a different style of recording that I did. If you have any questions, send me a message on Teams or attend a tutorial. or send me an email. Thanks, everybody.